Hello everyone, and let me walk you through this week's highlights on mechanical waves. So to start off, I want you to think about driving in a car on a very rough road. You're in your car seat, and as you go over this rough road, you're kind of bouncing up and down as you go. Well, what if we plot out our position as a function of time? So we start at high, and then we bounce down low, and then we bounce up high again, and then low, and so on and so forth. Well, there's a lot of information that we can get from this type of plot when we plot a position as a function of time. So for starters, let's talk about amplitude. Now, amplitude is the height above the equilibrium point, not from the lowest point to the highest point, from the equilibrium point. So here is from that base equilibrium point up to the highest point, or you could think about it from the equilibrium point down to the lowest point will also be the amplitude. Period T, capital T, this is the time for one full oscillation. And so we can measure this by going from peak to peak, right? So one full oscillation, you start here, you go down, you come back up again, and the time it takes for that to happen is the period. You could also do trough to trough as another way to also calculate the period here. Now, frequency, this is a calculation from the period. You can't get it directly from the plot, but you can use the period to calculate this. So here we have period, which is capital T, is the seconds per oscillation. And frequency is just the inverse of that, oscillations per second. So it makes sense when we convert from frequency to period or period to frequency, we can just use these equations. Frequency is one over the period, or period is one over the frequency. So I want you to think, anytime you have the frequency, you always have the period, and anytime you have the period, you always have the frequency, because all you got to do is just take the inverse. Now, frequency does have a nickname unit, and that is hertz. So frequency is oscillations per second, and hertz is Hz, is the symbol that you'll use for that. There is no nickname unit for period, it's just seconds per oscillation, or you can just do seconds, because oscillation is easy. All right, this is another plot, but in this case, we're just seeing a position plot of this. This is like a picture or even a video of a wave. And in this case, you can see the wave here. The length from trough to trough or peak to peak is no longer the period. This is the wavelength, the length of one full wave. Now, if we were to look at this part of the slinky, and we were to plot this position as a function of time, you can imagine in this video that this part of the slinky is going to go down and back up again, and then down and back up again. Well, we can plot that vertical y position as a function of time, and we arrive at a very similar plot. Here, as a function of time, that peak to peak measurement is now the period of the oscillation or the wave, and not the wavelength. So just pay attention to what kind of plot you're looking at, whether it's a position plot or a time plot. That peak to peak or trough to trough measurement will be different depending on which plot you're looking at. Well, let's get some equations here to try to calculate what these periods are going to be. Let's start with the period of a spring. So you can imagine we put a mass on the end of a spring, we pull it down, and we release it. So you see this oscillation here. Well, there's a period, there's a time it takes for it to go all the way back up and all the way back down again. And that is, again, symbol t. We're going to use subscript s for spring. And that just equals 2 pi times the square root of m over k, where m is the mass on the spring and k is the spring constant. So what is the frequency of this oscillation? Well, you're right. We have the period, we got the frequency. So it's just going to be 1 over that period. Let's move on to a pendulum. So the period of a pendulum, we use p for pendulum, is equal to 2 pi the square root of L over g, where L is the length, the full length of that pendulum, and g is gravity. So on the surface of Earth, we'll use the 9.8 value. So how will changing the mass on the end of this pendulum affect the period? Now, for a spring, it was right in their equation. But here, for a pendulum, there's no mass in the equation. And that might feel a little weird, so let's think about it. If I make the mass here bigger, isn't the force of gravity going to be larger? Meaning that's going to be pulling it down with more force, so shouldn't that make it go back and forth quicker? Well, more mass also means more inertia, and inertia is resistance to change in velocity. So it's going to resist the change in velocity more. And it turns out those two effects perfectly and exactly cancel each other out, meaning that an increase of mass or even a decrease in mass will not affect the period of this motion going back and forth. Now, I want to highlight that this equation really only works at an amplitude below 15 degrees. So when you release this from rest, be sure the angle is less than 15 degrees, so when it swings back and forth, this equation is still valid. This was derived with calculus, and so I can't show you, or I'm not going to show you where this comes from, but there was an approximation made for small angles here when this was derived. Now, it's not that far off if you go higher. For instance, if you pull this all the way up to 90 degrees and release it, so it swings all the way down to the other side at 90 degrees, to have an amplitude of 90. The period is only 18% longer or bigger than it is below 15 degrees. So it's not terribly far off, but this equation is really only really accurate below 15 degrees amplitude. All right, what about how fast waves are traveling? We can use this equation. The velocity of the wave is equal to the wavelength. So this is the symbol for wavelength, lambda, the Greek symbol, times frequency. So let's look for air. So let's say we measure, for a sound wave, we measure or let's say we emit a frequency of 160 hertz, and then we measure the wavelength of that sound wave to be 2.13 meters. Well, we can multiply these two together, right? Wavelength times frequency gives us wave speed, and we end up with 340 meters per second. Well, let's emit a different sound frequency, 264 hertz. We measure the wavelength of that sound to be 1.29 meters. Multiply those together, and we arrive at, also 340. We do it for a bunch of other frequencies and measure the wavelength, and we also get 340. So what's great about this is, for a gas, the speed of sound is the same regardless of the frequency or the wavelength. Okay. Now, that means that it's going to be the same. It doesn't mean that the sound of the speed of the wave won't change. So for instance, on hotter air, the sound wave will actually travel faster than it is in colder air. We also have an equation for that. The speed of sound is equal to 331 times the square root of T over 273. Now this T, we got to be very careful. This is the air temperature, not the period, okay? This is the air temperature in Kelvin. So you can see that this 340 meters per second, this is more like room temperature, 20 degrees Celsius or so, or 293 degrees Kelvin, which we plug in here to calculate what that sound velocity is going to be. Sound intensity. So sound actually transfers energy, and the intensity of the sound, the symbol I, is what tells us how much energy per second the sound wave is sending over a given area. So that intensity is proportional to the sound pressure amplitude, okay, squared. So just for example, if I were to double the sound pressure amplitude of a sound wave, by how much larger is the intensity going to change? Well, if I double this amplitude, it's squared. So it's going to make it 4 times as large, because 2 squared is 4. Now, will we hear the sound as 4 times as loud? We might think so. It's sending 4 times as much energy than it was before, but our ears and brain interpret sound a little bit differently. In fact, after many studies on sound perception, the sound must increase intensity by a factor of 10 for us to perceive that sound as being twice as loud. So as opposed to talking about the intensity of sound waves, we developed a whole new system to kind of classify how loud something is, and we call that the decibel system. This is a whole other complicated equation that we use to determine how loud something is using this decibel scale. So decibels uses this Greek symbol beta. It's equal to 10 times log base 10 of I over I0. Where this is the sound intensity that we want to know the decibels of. And I0, this is this reference intensity. This is the softest intensity that the human ear can hear. So this just helps us to quantify how loud something is kind of to the human ear, as opposed to how much energy is being transferred. So I pulled a bunch of numbers from the textbook here. So when the decibels is 0, the intensity of the sound to cause that is 10 to the negative 12th. And this is the threshold of human hearing. You really can't hear anything at 0 decibels. Now, when you go up to 20 decibels, this is the intensity in order for it to be at 20 decibels. This is like a whisper from 1 meter away. 60 decibels is this like normal conversation. 120 decibels is like a really loud rock concert, like almost painful. And 160 decibels is like you're bursting your eardrums. Now, what's really amazing is that our ears are able to hear very loud things before it gets hurt, and able to hear very, very soft things. So this is 10 to the negative 12th energy transfer versus 1. Okay, so this is a huge range. Negative 10th is what we can really hear in whisper. This is a huge range of values of energy transfer, of intensity of sound that we can hear, which is really quite amazing. Let's do an example. So the sound of a dog's bark has an intensity of 3 times 10 to the negative 6th watt per meter squared. So how many decibels is this? So we can plug it into our decibel equation. Beta equals 10 log base 10 of I over I0. So I, which is the intensity of the sound, is 3 times 10 to the negative 6th. I0, which is 10 to the negative 12th. We plug that into our calculator, we arrive at 65 decibels. Now there's something I want to point out to you in your calculator. Be very careful because a lot of different logs, okay? So here is maybe a calculator that you might be familiar with or using. Here it just says log. This log is actually log base 10. There's another log, ln. This stands for natural log or log base e. So before you solve these problems, I want you to do this test. You do your calculator, so do log base 10 of 10, and this should give you the value of 1. If it does, then that button you're pushing on your calculator is in fact log base 10, and you can continue to do the problems with that. If it's not, do the test on a couple other buttons to be sure that it's log base 10 in order to be able to plug them in here to solve the problems. Here's a summary slide for this highlight video with the equations and some of the graphs. Take a look at this. Let's get started.